We're used to seeing equation in what's called their explicit form. In other words, y is written in terms of x. You may see something like y is equal to 2x plus 3, or y is equal to 1 over x plus 1. Y is completely in terms of x. When we want to find the derivative of that, it's easy to find dy with respect to x. However, when a function is not written with one variable in terms of another, we refer to this as what's called the implicit form. If we want to differentiate that form, we must first rewrite the equation explicitly. So for example, if I have something like x, y plus y equals 1, and I want to differentiate that, I can factor out a y, which leaves me with x plus 1 equals 1. And then I can solve for y to be 1 over x plus 1. And from there, I'm able to take dy with respect to x. However, there are times that it's not possible to write the equation explicitly. If there's a squared term, for example, we don't know whether it's the positive square root when we take it or the negative square root. However, we can use something called implicit differentiation to solve these types of equations. For example, suppose that I wish to find the derivative with respect to x of the function y squared, where y is assumed to be a differentiable function of x. We can denote y as a function g of x, and therefore dy over dx is simply g prime of x. So if I want to find the derivative with respect to x of y squared, notice what I'm really doing here is I'm finding the derivative of g of x squared. And using our power rule, we know that to find the derivative there, I'm going to do 2 times g of x times g prime of x. And from there, I can get 2 times g of x is y, as we defined it here. And then g prime of x is going to be y prime, or dy dx is also the same thing as y prime. Well, from there, we could further use differentiation, just like we did with that expanded power rule or the chain rule. Let's apply it here in this example. If I want to find the derivative at a point, say of this function, that I cannot explicitly define, then to take the derivative dy over dx, I'm going to take the derivative dy dx of the entire function. So of x squared plus y squared equals 25. I'll take dy with respect to x of x squared plus dy with respect to x of y squared, and then d with respect to x of 25. I can take the derivative of the first one with respect to x because it is with respect to x, so that's going to be 2x. And then here, I'm going to apply 2y and then y prime, or dy dx. And then the derivative of a constant is 0. My goal then is, remember, y prime is just another way to write dy over dx. So if I want to know the value of dy over dx, I can now solve this function by subtracting 2x. And I have 2y times y prime equals negative 2x. I can divide both sides by 2y. And so I get y prime. Again, that's nothing more than dy over dx is negative x over y. If I wish then to define that derivative at those two specific points, I can evaluate dy dx at the point 4, 3 by plugging in negative 4, 3 at that point, and I can find dy over dx at the point 0, 5 by also plugging in negative 0 over 5, which is just 0. If I graph these values, notice that x squared plus y squared equals 25 is a circle with radius 5. And at the point 4, 3, I'm going to have a tangent line with a slope of negative 4. And at the point 0, 5, notice that slope is indeed going to be 0 because it's a horizontal line. Let's look at a second example here using differentiation. Notice in this case, we're going to also have to apply the product rule. If I want to find dy dx, remember I can also call that y prime, I'm going to differentiate each piece here. I'm going to have to apply the product rule in both cases. So I'm going to have the first term times the derivative of the second, which is y prime, plus the second times the derivative of the first, which in this case, the derivative of the x is just x. And that is taking care of this first piece. Then I'm going to apply the same thing to this next part. I'm going to do the first term times the derivative of the second, which is going to be 3y squared y prime, plus the second y cubed times the derivative of the first, which is 2x. And that's going to equal 0. As I simplify here, I get x, y prime, plus y, plus 3x squared, y prime. Then I'm going to have plus 2xy cubed equals 0. And I forgot my y prime here. That was already up here. Notice these are like terms because they both have a y prime. So I'm going to pull out my y prime there, which leaves me with x plus 3x squared y squared. And then I'm going to move the other pieces to the other side. And when I subtract those, I get a negative y minus 2xy cubed. Again, my goal is I'm trying to find the derivative of y with respect to x, or y prime. So I'm going to divide both sides here by this term. And I end up with the derivative dy over dx is negative y minus 2xy cubed all over x plus 3x squared y squared. Let's look at one more example before we jump into some word problems like this. If I want to find dy dx in this case, don't do anything different. I'm still going to take the derivative of this first term, but the first thing I'm going to do is I'm going to rewrite it using exponents. And then I'm going to take the derivative of everything. So for this first term, I'm going to end up with 1/2 x to the negative 1/2 minus 1/2 y to the negative 1/2. And don't forget that y prime that must be there, or dy dx. And when I take the derivative of 16, I simply get 0. Again, this is what I'm trying to solve for, is the y prime. I'm going to move my 1/2 x squared to the other side by subtracting. And I end up with negative 1/2 y to the negative 1/2 equals negative 1/2 x to the negative 1/2. My 1/2s end up canceling and the negative along with it. And I still have my y prime here that I'm trying to solve for. And so I end up with y prime is going to equal x to the negative 1/2 divided by y to the negative 1/2. And to get rid of the negatives, I can simply flip it and I get the square root of y over the square root of x is that derivative. Please do note that it may seem counterintuitive that we're not listing d over dx, mainly because that's going to end up as a value of 1. So we stick strictly to that y prime that we need. And the reason this becomes important is because when we want to look at how two or more variables that are dependent on time affects things. So consider something like y equals 5x plus 1. If x and y were both dependent on time, if we wanted to take the derivative of this with respect to time, then I would do dy over dt is going to equal the derivative of this side of the function with respect to time. And so on this side, I would get dy dt. The derivative of 5x with respect to time is going to be 5, and then dx with respect to dt. The derivative of 1 is going to be 0. And so what you can see is that the rate of change at which y changes is 5 times that as fast as that of x. They are related to one another. Let's look at this in something that might make a little more sense in terms of word problems. If we have a balloon that's being inflated by a continuous flow of air, and that rate of flow of air is 2 cubic inches per second, we want to know how fast the radius of the balloon is growing when the radius is 3 inches. Well, we know that the change in volume with respect to time is 2 cubic inches per second. What we want to find is the change in radius with respect to time. We have to know some formulas here. The formula for a sphere is 4/3 pi r cubed. What we want to know is the change in radius with respect to time. So I can differentiate both sides with respect to time, because that's what I'm trying to calculate. And just like we did with x and y, I'm going to have dv over dt. When I take the derivative here with respect to time, remember, we know the radius is changing with respect to time. So we're going to have the 3 will bring out front, which will make that cancel. And we end up with 4 pi r squared. But then we also have to take the derivative of the radius with respect to time. Fortunately, we already know the value dv over dt is 2 from the given information. And we've also been asked to calculate this specifically when the radius is 3. So I'm going to plug in 3, and then I can solve for dr over dt. I end up with 2 is equal to 4 pi times 9 dr over dt. And when I solve there, I'm going to end up dividing both sides by 36 pi. And dr over dt is going to be 0.018 inches per second. That's the rate at which the radius is changing with respect to time when the radius is 3 inches. Consider here we have an airplane flying in a circular pattern, sort of like a holding pattern, and we know that the radius of that pattern is 2 miles. The path can be described by the equation of the radius of a circle. And when the plane is at the point x is the square root of 3 and y is 1, it's traveling north at 300 miles per hour. How far is it traveling to the west? Consider what's happening pictorially here. If we look at a diagram, we know the plane is flying in a circular pattern. When we are at the point that x is square root of 3 and y is 1, notice that the plane is traveling both north and it's also traveling west. They've told us the rate at which it's traveling north. We want to know the rate at which it is traveling west. We have an equation that describes the location of the plane. It is the holding pattern x squared plus y squared equals 4. So we can differentiate this. I can take the derivative 2x times the change in x with respect to time, because I'm looking for how fast it's traveling with respect to time, plus 2y times the derivative of y with respect to t. And when I take the derivative of 4, I get 0. Here, the y direction is north. We know that that value is 300. So I have 2x dx over dt plus 2y times 300 equals 0. But they've also told us the x and y value that we're concerned about. We know that x has the value of the square root of 3. And we know that y has a value of 1. So we end up with 2 square root of 3 dx over d, and that should be a dt here, plus 600 equals 0. Subtracting 600 from both sides, we have 2 square roots of 3 dx over dt equals negative 600. And when we divide by 2 square roots of 3, we get a value that the plane is traveling west at negative 100 square root of 3. It's going in the negative direction. And if we calculate that, that's approximately 173.2 miles per hour. Another place that can come in handy is if we have things traveling in two different directions and we want to know how much they're spreading apart from each other. If we have two cars traveling towards an intersection together, one from the Y and one from the X direction as listed here, neither driver plans to stop. We want to see how quickly they're coming at each other. Car A down here is traveling 40 miles per hour, and car B is traveling 60 miles per hour. How fast is the distance between the two changing? Well, this is a triangle, so we know that the hypotenuse is going to equal the two sides squared and their sum. We can differentiate this because we want to know how fast this is changing. So we're going to have 2s ds to dt is going to equal 2x dx to dt plus 2y dy to dt. Should be over dt. In this case, what we know is that we're trying to find ds to dt. So when we solve this, we're going to divide everything by 2s, but notice the 2's all cancel out. So we end up with ds over dt is going to equal x dx dt plus y dy dt all over s. Notice that as x and y are decreasing, their velocities are going to be negative. And so we can substitute in the values that are given to us. We know that the car right now in the x direction is 0.7 miles from the intersection, and it is moving at a rate of 60 miles per hour, negative because it's going in that direction. Plus, the second car is 0.5 miles from the intersection, and it's traveling at 40 miles per hour, all divided by our S value, which at that moment, if we plug it into our original formula, is going to be 0.9. If we calculate all of that, 72.2 miles per hour we get, and it's negative, which tells us that the distance between the cars is decreasing at 72.2 miles per hour. The last one I want to look at is an example that applies directly to business. If you have the cost of production that you're looking at, you can consider two categories, both labor and capital. The cost of labor is typically what you're considering is what you're paying folks. And then the cost of capital is how much you're putting into the products, the materials that you're buying to create your product. The relationship that this often references is called the Cobb-Douglas production formula, where P tells us the number of units produced. We have C and A that are constant values, and then our X and Y represent the labor and the units of capital respectively. So let's see where this would apply and how we might use implicit differentiation to help us calculate something in business. If we have a firm that knows their level of production to be P equal to 20 x to the fourth, y to the 3/4, and again, they are using x to represent labor and y to represent capital. And currently, they have given us a rate of 16 units of labor and 81 units of capital. So those are X and Y respectively. Then they're telling us how much labor is increasing by, and we want to know what the capital change must be to maintain the current level of production. Well, our current level of production, we can calculate from our formula by plugging in the X and Y values given. They've told us that we're using 16 units of labor and that we are using 81 units of capital. So when we calculate this, we get that our units of production are 1,080 units. Note, we want to keep that level of production constant. If we simplify this, we can view this a little differently in terms of we can consider that we always want our production to be this value, regardless of what, in this case, X and Y become. We can divide both sides by 20 here, And so what we can say is that we want x to the 1/4, y to the 3/4 to always be 54. But we've got to figure out how to change our level of labor, or I'm sorry, our level of capital change in units per month, knowing how much our labor is changing. In order to do this, we're going to differentiate both sides with respect to time. When I differentiate 54 with respect to time, we're going to end up with 0. And then on this other side, we're going to end up having to apply the product rule. On the left, we end up with 0. And then here we have our first term and our second term. So we're going to have first times the derivative of the second, which is going to be 3/4 y. When we subtract 1, we're going to end up with 3/4 minus 1, which gives us negative 3/4. And then don't forget, we're going to need that dy dt. And then we're going to have plus the second term, y to the 3/4 times the derivative of the first term, which is going to be 1/4 y to the negative 3/4. And then we will have 1/4 x to the negative 3/4. And then we'll have dx over dt. When we simplify this, we end up with 3/4 x to the 1/4, y to the negative 3/4. And I'm sorry, that should be negative 1/4 in both of these when we subtract 1. When we subtract 1 from 3/4, we get negative 1/4. And then we still have our dy dt. And then we have 1/4 y to the 3/4 x to the negative 3/4 dx dt. But notice we've already been told that x is 16. So we have 16 to the 1/4, and we've been told that y is 81. And then we still have our 3/4 out here. And then for our dy dt, that's what we're trying to solve for, because we want to know how much the capital has to change. And so then we have 1/4, y again is 81 to the 3/4, and x is 16 to the negative 3/4. But we've been told that dx over dt is 4. And as we calculate all of this, remember this equals 0. So we end up with negative 1/2 dy dt equals 27 over 8, which we can reduce and simplify to get dy over dt is equal to negative 27 over 4. What that means is the capital must decrease at a rate of 27 over 4 to keep the level of production the same.